So today we're going to talk about cryptography, which is an extremely cool topic at the very intersection of application and theory. What is cryptography? Well, if you break it down, cryptos means hidden or secret. Graphene means writing. So it's like the study of secret writing in some sense. Study of secure communication in the presence of third parties. Like a very well-known situation, like you want to send an email to your friend, you don't want other people to read it other than your friend. You want to send your credit card information to your bank or Amazon. You don't want other people to learn that information while you're sending it, right? So usually there are two parties. So let's say here are the two people. So who are these people? Cersei and Marjorie, I think. So Cersei has some message to Marjorie. She wants to tell her in secret yeah, there we go. It took her some time to say it, but yeah, so she wants to say this. She could, of course, and like we're assuming they're not like physically together, they're far apart, so she has to communicate this somehow through some channel. She could just send this to her, but the problem is there are third parties involved that can intercept this message. Right? It's like he knows everything, right? So this person, by the way, we'll usually call him an adversary or an eavesdropper. So you don't want the adversary to learn anything about what you want to send. So for this kind of situation, what we try to do is first encrypt our message somehow to some other message, to some message that looks garbage, hopefully, to an eavesdropper. So you send that garbage-looking message over this channel, and then hopefully there's also some decryption method that allows Marjorie to decrypt and get the original message. So now, like, this is a very basic scenario in cryptography, and definitely cryptography studies this situation, but actually cryptography is much more than this. So in general, you could say it's the study of protocols that avoid the bad effects of adversaries, whatever those bad effects might be. And you can study some very, very interesting questions in cryptography. For example, you can ask, can we have secure online voting schemes, right? That would be nice if we didn't have to physically go to some place to do our voting every time. Can we have digital signatures? So can I demonstrate the authenticity of some digital document to you? The way you physically sign a document, can we also replicate that in the digital world? You can ask, can we do computation on encrypted data? So suppose I own some company, some small company. I have some users, information about users. Now I keep that database. I can keep that database maybe on the cloud somewhere. But of course, I don't want other people to learn about that information. So I encrypt my data, my database, and then put it on the cloud. But then I still want to do computation on my data, right? So I need to be able to do computation on encrypted data. Can I do that? So that's a very interesting question. Suppose I prove the P versus MP problem, like P equals MP or P not equal to MP, or I prove the Riemann hypothesis. So I'm pretty proud of it. Now I want to share this result with you, but on the other hand, I don't really trust you. Okay, so I think like if I just show you the proof, you're just going to steal it and publish it yourself and steal the fame. So is there actually a way for me to prove to you that let's say P equals MP, without giving you any information, without you learning any information about the proof. Okay? So cryptography actually studies all these different kinds of questions. It turns out like you can do surprising things. So basically, the answer to all these questions are yes. Like you can do these kinds of things using smart cryptographic protocols. So some reasons to like cryptography. Well, as I said, like there are pretty cool stuff and unexpected things that you can do. Has many important applications. So actually, this kind of stuff is being used, in the real world. It's very fundamentally related to computational complexity. In fact, you can say computational complexity, in some sense, revolutionized cryptography. And now the two areas are very much interrelated. Can't really separate them from one another. It's a place where you want to make use of computationally hard problems. So you might ask, why do we try to prove that some problems are hard? We actually want some computational problems to be hard. Because without computationally hard problems, a lot of the cryptography that we use today basically goes away. And of course, there's a good math as well, like number theory. So that's the main reason to like cryptography. OK, so the plan for today is going to be actually first do a review of modular arithmetic, because it's going to be really crucial when we later talk about first private secret key cryptography and then later public key cryptography. OK, so first we're going to do modular arithmetic, and then we're going to discuss these two types of cryptographies, and I'll explain what they mean when we get there. But first, very quickly, let's review modular arithmetic. So one way to view modular arithmetic is as follows. You can say, well, my universe is the integers, and I'm going to say two elements in my universe A and B are mod M equivalent if M divides A minus B, right? What you already know. The plus, when we do plus, is the addition in the integers. So I added 5 plus 8 is 13, 1 plus 6 is 7, and check if they're mod 6 equivalent or not. You can do multiplication just the same way. Now, here's another way to view it. You can say, well, my universe is actually going to be the set Z sub M. So it's the elements 0, 1, 2, up to M minus 1. And we're going to define now our operations, plus, and so on, multiplication, and so on, within this set. So I can define a plus within the set, and then get this nice-looking table, the kind of table that we've already seen on Thursday. And then you can say, all right, so every element in the integers now really corresponds to some element. In this case, Z4. We have here we're working in Z4. So when we write 5 is mod 4 equivalent to 9, what we're saying is really 5 and 9 correspond to the same element in Z4 in this universe. And when we write something like 7 plus 2 is mod 4 equivalent to 1 plus 12, we could equivalently write it as 3 plus 2 equals 1 plus 0 in Z4, right? So this plus now is going to be in with respect to this table here, similarly here, and the equality is just the equality of the elements in this set. Okay, and you look at this table, you see that it's quite nice. Every row and column is a permutation of the elements. So you could also do subtraction, for example. So when we do like 1 minus 3, what do we really mean? We mean 1 plus minus 3. But then what is the meaning of minus 3? Well, minus 3 is just the additive inverse of 3, right? So an additive inverse, it's the element x such that 3 plus x is equal to 0. And 0 happens to be the additive identity, right? So it's the x such that 3 plus x is equal to 0. So, and if you look at this table, you know, what is x such that 3 plus x is equal to 0? Well, it's 1, right? So again, 1 minus 3 is 1 plus minus 3, which is 1 plus 1, because minus 3 is 1, and that's equal to 2. And you can see every element has a unique additive inverse, and things are nice as we expect them to be. Now you can say, okay, what about multiplication? Yeah, sure, we can do multiplication. We can create our table for multiplication. See 2 times 3 equals 2, for example. But then you say, okay, now let's do division, 1 divided by 2. Well, what do you mean by 1 divided by 2? What I mean is 1 times 1 over 2, right? And here, this 1 over 2 is really the multiplicative inverse of 2, right? So it's the x such that x times 2 equals 1, where 1 is the multiplicative identity. The thing is, there's no such x. So in this particular situation, we see that not all elements have a multiplicative inverse. So we say we can conclude Z4, this guy is not a good universe with respect to multiplication. So in general, which elements do have a multiplicative inverse? Let's say if we are working in Zm. So we've again seen this. We've all seen this last time. So an element x in Zm has a multiplicative inverse if and only if the greatest common divisor of that element x with m is equal to 1. Okay, so if I take my universe Z4 and I look at all the elements that are that have GCD 1 with m, then I have to erase 0 and 2, get rid of those guys, and what remains is 1 and 3. And from that, I can get this smaller table with elements 1 and 3. Okay, so in general, we have this notation. We define Zm star basically to be the elements of Zm that have a multiplicative inverse, or such that GCD of x and m is 1. Now, Zm star is nice. It behaves nicely with respect to multiplication. So just like Z4, when we looked at Z4, it behaves nicely with respect to addition. Everything has an inverse. The rows and columns are like permutations of the elements. Zm star, in this example, ZH star, for example, behaves very nicely with respect to multiplication. Everything has an inverse. The rows and columns are permutations of the elements. When m is a prime, it's easy to see what Zm star is going to be, right? The only element that we have to remove is 0. Other elements are going to be co-prime with m. And then we make this definition. We say phi of m is going to be just the size of Zm star, size of this universe. Okay, so we know when p is a prime, phi of p is simply p minus 1. And hopefully by now you've all proven the fact that for p and q distinct primes, phi p times q is p minus 1 times q minus 1. And then there was a very important theorem that we saw last time. So for any element in the universe Zm star, if you raise that element to the power of the size of the universe, like phi of m is the size of the universe, then you will always get 1. Okay? Another way to say it, like if you want to work in the integer universe, you can say for any a and m such that the GCD of a comma m is 1, a to the phi m is mod m equivalent to 1. And A special case of this is when m equals a prime number, then it's called the Fermat's little theorem, not last. Fermat's little theorem for p prime a to the p minus 1 is equal to 1, or equivalently, for any a that is not divisible by p, a to the p minus 1 is congruent to 1 mod p. Okay, so you can check your answer for the quiz here. Okay, so we've discussed, addition, subtraction, multiplication, division. Another very important operation is exponentiation. So how does exponentiation go in the modulo world? So let's take Z8 star. Here it is. And let's take every element and let's raise them to different powers and see what we get. So if I take 1, raise it to different powers, well, I always get 1, so that's not too interesting. If I take the element 3, I raise it to different powers, what I get is 3, 1, 3, 1, 3, 1, 3, 1, and so on. So that repeats like that. If I look at 5, that's 5, 1, 5, 1, 5, 1. 7 is 7, 1, 7, 1, 7, 1. So it's not very interesting, actually. But this could happen, right? So this kind of situation. Let's look at another table, Z5 star. So this is going to be a bit more interesting. So 1 is the same, of course. But if I look at 2 in this group, it's going to be 2, 4, 3, 1, 2, 4, 3, 1. And if I kept going, well, it would be 2, 4, 3, 1, 2, 4, 3, 1, 2, 4, 3, 1. We'll just repeat that. Once I go back to 1, you see, after that point, I will just repeat. With 3, it is 3, 4, 2, 1, 3, 4, 2, 1, 3, 4, 2, 1. Again, once I come to 1, I will repeat. Well, with 4, it is 4, 1, 4, 1, 4, 1, 4, 1. Now, here's the interesting thing. So we know that a to the phi of m, the size of the multiplicative group, is equal to 1. So what is phi of m in this case? It's 4. So when I look at the powers 4, I should see a 1 in the corresponding location, and I do, which is good. And that means, like, if I go to now 8, and then 12, and then 16, and so on, I will again see a 1. Okay, because as we said, once you come to 1, you will just repeat these elements. So really, these green blocks basically, just repeat themselves. These are size 4, size phi of m blocks. So that implies that you can actually reduce the exponent phi of m. Okay, so if you have something like a to the power n, that's really equal to a to the n mod phi of m. Okay? Now, just notice here that this is, when we're working in Zm star. Now, it doesn't always work for an element A that is not in Zm star. So that's something to keep in mind. But if your universe is Zm star, this is true. So what that means is really, when you live in this universe Zm star and you're exponentiating elements, you can think of the exponent as living in the universe Z phi of m. Okay? So the exponent, you can think of it as living in the universe Z phi of m. Or actually, you can also think of it as sometimes Z phi of m star if you are just interested in the elements that have an inverse. You can just restrict yourself to Z phi of m star as well. So example, when m equals 5, phi of m is equal to 4, you have an element 4 in Z5 star. You do like 4, 1 plus 3. Now in the exponent, I just treat this as Z phi of m. Right? In Z phi of m, in Z 4 basically. 1 plus 3 is equal to 0. So 4 to the 0, that's equal to 1. If I do, let's say, 4, 3 times 3, I can view this 3 as like in Z5M star. The inverse of 3, if you check, is 3 itself. So 3 times 3 is going to be 1. So 4 to the 1 is going to be 4. Now, this is important. We're going to use this. So just keep in mind that when we are in the universe of ZM star, the exponent, think of it as Z phi of M. The universe is in the exponent Z phi of M. Okay. Just going back to this little definition let me make. So 2 and 3, if you look at 2 and 3, you see that as you raise it to different powers, you generate all the elements of Z5 star. So when that happens, we call that element a generator. 2 and 3 are generators because you look at the green boxes for 2 and 3, they have all the elements of the universe. Okay, so this is also discussed in the homework. Now, one reason that we like to work in the modular world in the context of cryptography is because some very natural functions in the modular world turn out to be one-way functions. So what does that mean? So a one-way function is basically, at an intuitive level, a function that is easy to compute, computationally easy to compute, but computationally hard to invert. Example, multiplication. Given 2 primes, P and Q, you can multiply them together efficiently, no problem. Given P times Q, some number that's product of 2 primes, if I ask you, tell me now what the P and the Q are, this seems a computationally hard problem. So in cryptography, it's reasonable to try to encode your messages using some sort of one-way function. Why? Because, I want to send a message. I'm going to encode that message somehow and get an encoded message. And I'm going to send that encoded message over. Now, the adversary sees that encoded message. Okay? So hopefully, he won't be able to take that encoded message and invert it to get the original message. Right? So at a very high level, I'm being vague here, but at a high level, you can expect that you would want your encoding scheme, your encoding algorithm, to be somehow one way. Whatever, we can define one way more formally, but yeah. And when we are in the modular world, seems like some very simple operations seem to be one way. So I'm going to give you 2 examples. And we're going to use these examples later on. But let me start actually with just a regular function over, let's say, the natural numbers. And this is going to be the exponentiation function. So exponentiation function takes some base b, some exponent e, and just computes b to the e, base to the exponent. Now, I can actually view this in 2 different ways. I can get like 2 different functions out of this. If I fix an exponent e, I can talk about the function exp of b, which is b to the e. So let's say you fix the exponent to be 3. Then the first one of these would be basically cubing b cubed. And then I can also look at it the other way around. I can fix some b and then say x sub b of e is going to be b to the e again. And let's say, if I fixed b to be 2, that would be like you're exponentiating, you're taking 2 to the power e. So the exponentiating function. Now, these functions, these 2 functions, are basically easy to compute. and easy to invert in, if you're not in the modular world. So if we look at the inverse of the first one, given some number of the form b to the e, you know what e is, what the exponent is. You want to compute b. What is that like? Well, that's like computing the eth root of b to the e, right? So again, if you fix like 3 in your head, I give you some number which is b cubed. I ask you, give me the b. That's like computing the cube root of that number. The other one, the inverse of the second one, xp e, is like, okay, you are given some number of the form, again, b to the e. Now you know the base b, and I tell you now, I ask you compute the exponent e. Well, that's like computing the log base b of b to the e, if I want the exponent. Right? And as I said, both of these inverse functions, the first one is actually not trivial. You can think about how you would take eth root, cube root, for example, or the square root of. It's not trivial, but you can do these things efficiently. Now let's look at the same functions, basically, but now in the modular world. Okay, so the first one is going to be called the RSA function. And this was going to be like exp when you fix some exponent e. Again, think of e as 3, okay, in your mind. So this is like the cubing function, the RSA function, b cubed. And the inverse is going to be like taking the eth root or the cube root, let's say. Now, to be precise, our setting is going to be, so we're going to be in the universe Zm star, where m is going to be some composite number. Why composite? Wait for it. So I'll say why it's composite, but just for now it's composite. Now you fix some exponent, e. Now this exponent, you see it's in z phi of m, right? So in the exponent, the universe is phi of m. And actually, I want an exponent that has an inverse. So it's z phi of m star. Then the RSA function is basically the function that does b to the e for a given input b. Right, again, think of e, fix e to be in your mind 3. So this is the cube function, b cubed. The inverse would be taking the cube root if e was 3. Okay. Now, if I want to compute b to the e, how do I do it? So we've seen this on Thursday. We've seen how to do fast modular exponentiation. So that we can do, easy. Second one, inverting this, seems hard. I cannot prove to you it's hard. There's no such proof. All we can say is we've tried for a very long time, and it seems hard, like we cannot do it. Now here's a little note. Here, when I say like, let's say this inversion, take the cube, let's say cube root. You know m, I have to tell you m and e, but I don't actually tell you phi of m, okay? Because if you knew phi of m, actually you could do the inverse efficiently. Okay, it turns out. I will discuss this a little bit later on, but just take this as a fact for now. And this is why now, if you ask why composite, why are we talking about composites? Well, if m was a prime number, p, then I know phi of p is p minus 1. And then I can do the inverse efficiently. So this no longer becomes a one-way function. Okay, so we need m to be a composite number. Now the second example is going to correspond to this function, where you're given the base, you fix some base, let's say like something like 2 or 3, whatever, and you're exponentiating that base. And the inverse will be like taking the log base b. In the modular world, we're going to look at this corresponding function where the universe is zp star, where p is a prime number. And then we fix some generator b in zp star. This is going to be our base, the fixed base. And then I'm going to use this notation exp for this function. So for this fixed generator b, given as input some exponent e, you take b to the e. And the inverse would be, given b to the e, and p and b as well, what is the corresponding exponent? And again, the exponent lives in the world z phi of p, right? So this is again easy to do, b to the e. The second one, the inversion seems hard. Again, I cannot prove it, but it seems hard. All right, so those two functions are actually quite important, and we're going to make use of them later on in the lecture. But now let's actually start our discussion on private key cryptography. So we're going to first talk about private key cryptography. This is basically, you can think of this as like the cryptography of the old days, of before, let's say, World War II. And then later we're going to talk about public key cryptography, which is like, you can think of it as a modern cryptography, like cryptography after World War II, after computer science was born. So private key cryptography, so this is like cryptography from the old days. If I said like, okay, you have some letter, you have like physically written some letter, and you need to transfer that letter to some other place, how would you securely try to do this? The first thing that's going to come to your mind is the following, right? So you're going to say, okay, suppose like I share some key with the person that I'm trying to communicate with. Then what I can do is I can take my message, put it in a box, lock it with my key, send that box, and then, since the other person also has the key, they can just open it and get it. But we are the only people who have this key, so we are the only people who can unlock this message. Hopefully no one else will be able to unlock it. Okay? The trouble is, there's one downside. You have to agree on a key, this key pair beforehand. So really, before you do any kind of communication, there must be a secure way of exchanging this key. So maybe, one day you come together and you share this key and then you go apart. So you can do it physically, exchange it physically, maybe in a secure way. But this is the setting, okay? This is the setting that we're going to work with. Now, if I took that picture and made it a bit more formal, use some notation, we can say, okay, we have a message M that we're trying to send. We're going to have a key, call it KA, and the recipient is going to have a key K sub B. Usually they're going to be the same key actually, or they're going to be very related to each other. What I'm going to do on this side is I'm going to take the message and the key, I'm going to apply some encoding algorithm and produce a ciphertext, an encoded text. I'm going to then send that encoded text over this channel, which is assumed to be insecure, so there can be an eavesdropper that sees the C, but hopefully it will look garbage to that person. But on the other hand, you receive this ciphertext or encoded text, you apply your key to it, you have some decoding algorithm that will then produce you, hopefully, M, the message. Now this encoding function in some sense, again, you can think of it as follows. It should be in some way one way, right? Because I don't want the eavesdropper see C. I don't want him to be able to, from C, get the message or the key, right? And in private key cryptography, basically, you try to ensure that this is one way using the fact that the key is secret. Okay? So that's sort of your advantage over the adversary. While the key hopefully is secret, the adversary doesn't know the key, and that will allow me to make this encryption in some sense one way. He won't be able to go back because he doesn't know the key. Now, when we talk about security of cryptographic systems, so there are different cryptographic systems that try to implement this strategy, okay? And then you want to, of course, analyze the security of these systems. And when you're analyzing the security of these systems, it's always best to consider worst-case conditions. You don't want to take any risks, right? So we're going to assume that the adversary knows everything except the key and the message. So he completely sees the ciphertext, the encoded text, and he completely knows the algorithms that you're using for the encoding and decoding. Okay? So he knows the system that you're using. He sees the ciphertext, but he doesn't know the key or the message. You can even make further assumptions, actually, to make sure you're even more secure. You can say, I'll even assume the adversary knows some of the message and the corresponding encoded text. Okay, and then try to build your crypto system that is secure even against such adversaries. We're not going to look at that, though. But we will assume that the adversary sees the C, the ciphertext, and knows the system, the crypto system you're using. So Caesar implemented one of the oldest implementations of this kind of cryptographic system. Was done by Caesar, actually. It's called Caesar shift. It's pretty simple. What he did is he took the alphabet, okay, and shifted by some number. Okay, so for example, if he shifted by 3, basically A then mapped to D, B mapped to E, C mapped to F, and so on. So you take the alphabet, shifted by 3 places, and at the end you put ABC. You do the similar thing for capital letters. And basically, this was how he communicated with his generals at the time. So if there was a message like this, you know, you can think that, well, it would be encoded. If I did shift by 3, it would be exactly encoded to this. And you might be like, wow, that looks pretty garbage. So maybe this was secure. So the key here, the key he's using is the shift number. The problem is it's very easy to break, okay? And you can break it just by brute force. Try every possible shift and see which one works. Okay, there's more sophisticated versions, I guess. Substitution cipher. So this time it's not like the letters are shifted by some number. This time you takes any permutation of the alphabet. Okay, it can be any permutation. And still, this is easy to break. Why is it easy to break? It's easy to break because you can look at, for example, letter frequencies. So if I know the message that's being encoded is English text, well, I can say, you know, in English, I don't know, the letter X does not appear a lot. So I will look at the ciphertext. And let's say I'll look at the letter that appears the least amount of time, the least number of times. So maybe that's Q. And I say, well, okay, since Q appears the least number of times, I can make now an educated guess that maybe Q corresponds to X, and so on. And I mean, I can do this kind of frequency analysis and basically break this. Is a much more complicated cipher, the Enigma machine that was used by the Germans in World War II. This was much harder to break, but at the end it was broken by the Allies. And it's said that this reduced the length of the war by at least 2 years. The fact that the Allies were able to break these machines. But we're not going to discuss that. You can ask, is there anything that is secure? So everything so far has been broken. So here's one crypto system that's actually perfectly secure. It's called the one-time pad, and this is the way it works. So we're going to say M is the message, K is the key, C is the encrypted message. And here's how we're going to encode a message. So we're going to assume that everything is encoded using 0-1 strings. Okay, so no letters, just zeros and ones. The message is some 0-1 string. I take a key, K, which is basically, think of it as some randomly chosen 0-1 string that has the same length as the original message M. And what I do is I basically take the bitwise XOR of M and K, to produce the ciphertext, the encoded text C. So what that means is that for every index, when you look at every index one by one, the ith bit of the ciphertext, the encoded text, is going to be simply the ith bit of M plus the ith bit of K mod 2. That's it. Another way to say it is, if Ki is 1, what you do is you actually change or flip the ciphertext at that position. If Ki is 0, you don't change it. So these are equivalent ways of describing the same thing. How do you now decrypt a message? Well, the decryption actually works the same way as the encryption does. Given a ciphertext, you take the same key and you XOR it with the ciphertext, and you will recover M. Why is that? Because we know the encryption is M XORed with K. Right? Then if I now look at the decryption scheme, which is to XOR C and K, well, C is, I know, M XORed with K, right? So I can write for C M XOR K, and then I'm XORing another K. Now this is going to be M simply because K XORed with K, this is going to be 0, the all 0 string. Okay. If you take 0 plus 0 mod 2, it's 0. If you take 1 plus 1 mod 2, it's 0. Okay, so the decryption works the same way as the encryption. And it can be shown in a very precise way that one-time pad is perfectly secure. Of course, you have to define what secure means and what perfectly secure means. But once you do that, you can show that it's perfectly secure. But at an intuitive level, let me try to convince you why it's perfectly secure. So notice that for any M, if you choose the K uniformly at random, then you can show that the C that's going to be produced, the encoded message, is going to be completely uniformly random. Okay? And this is for any M. For any M, if K is uniformly at random, C is uniformly at random. So really, if the adversary C is C, he learns nothing about the message M. It's like completely random message from his perspective. Okay, so that's like at an intuitive level. There's a way to formalize everything. The downside, of course, is you need to share a key that is as long as the message. For this to work, and you can ask, can we reuse the key? Use the same key to encrypt different messages. And that turns out to be a bad idea. There's a reason why it's called one-time pad. Okay? So it's one time only in the following sense. So if you were to use it, use the same key for 2 different messages, M1, M2, and produce 2 different encoded text, C1, C2, well then, the adversary sees these things. He can compute the XOR of C1, C2, which is going to be M1 XORed with M2, right? The K's will cancel each other out. Now, that's not gonna immediately give you M1 or M2, but if you have some predictions, some reasonable predictions about what these messages might contain, you can actually try to then use that to gain information about these messages. And in fact, during Cold War, some Russian spies, they were using one-time pad, and they made a mistake sometimes, and they used the same key for different messages, and the Americans were able to decrypt some of their code and catch some of the spies, actually. So you got to be very careful about these things. Yeah.
How would the adversary know that they use the same key? I mean, would certain patterns emerge, or would you?
Yeah, it's a good question. I mean, I don't know exactly how they knew, but if somehow you knew that, yeah, you could make use of it. And then there's a very important theorem here in this context, Shannon's theorem. You can ask, like, is it possible to have a secure system like one-time pad that doesn't use a key size that's as big as the message itself, right? So you really want this, for these kinds of things to be practical, you want the key to be as small as possible. And Shannon proved no. So he showed that if k is shorter than m, basically, an adversary with unlimited computational power could learn some information about m. Okay. Now, there are three questions, important questions that come up here that we're going to try to address. The first is, can we relax this assumption that the adversary is computationally unbounded? Okay, because that seems to be a very strong requirement. And it turns out that if we do relax it, and if we say, you know what, the adversary is going to be computationally bounded, is a reasonable assumption to make, it turns out it opens up a whole new world of possibilities when you do that. At the same time, though, there's a downside. Since we cannot formally prove the hardness of problems, these crypto systems then are going to be based on unproven assumptions, unfortunately. But yeah, the positives outweigh definitely the negatives. Then the second question is, can we find a way to share a random secret key over some insecure channel? Right? So we want to, let's say, apply one-time pad, but to do one-time pad, we need to share this random secret key. Can we do that over an insecure channel? And in particular, we're going to look at this question right now. Can we do that, assuming that the adversary is computationally bounded? And the third part is, can we get rid of the secret key sharing part? So the crypto system that I've been describing is, you have to share this secret key. Seems inconvenient. Like every time we need to communicate with each other, we need to agree on this key. So someone who doesn't know me, someone I don't know, someone who's never communicated with me, should be able to send me a message, send me an email, let's say, right? So can we do that? Okay. And this will be basically what we call public key cryptography. But the first, in the remaining, we're going to do these two things. First, let's do secret key sharing. Okay, so in the secret key sharing, we have two parties. They're going to communicate with each other back and forth, and hopefully end up with a secret key K that the adversary knows nothing about, right? So the adversary sees this communication in the middle, but doesn't really gain any knowledge of K. And we're going to discuss here the Diffie-Hellman key exchange protocol from 1976. So the idea here is, again, it seems reasonable to try to encode messages using a one-way function because you don't want the adversary to learn any information about the message. So let's take this one-way function that we discussed, the exponentiation. So let P be a prime, take some generator B, right? The exponentiation function is basically given some exponent as input. You want to calculate b to the exponent e, b to the e. Okay. So here's now the protocol in full. What we're going to do is, what Cersei is going to do is pick some prime p, pick some generator b in zp star, and pick some random r1 in z phi of p. So this r1 is going to be, think of that as the exponent, right? So that's why it's in z phi of p, it's in the exponent. And what we're going to send to the other side is going to be p, the b, the generator b, and b to the r1. Now here our hope is that b to the r1 is not easy to invert, right? So knowing p, b, and b to the r1, hopefully you're not able to guess what r1 is. So r1 is totally secret to you. You don't know what r1 is from this. That's the hope. That's the one-wayness of the exponentiation. Now on the other side, you get this information. What you do is something very similar. Now that you know p, you can now pick a random r2 in z phi of p yourself and send b to the r2, b to the power r2. And again, your hope is, the adversary is not going to be able to, by seeing this, is not going to be able to recover r2 or learn anything about r2. Okay, then we're basically done. What we're going to do, what both parties can do now is actually the following. So if you look at Cersei, she's just gotten b to the r2. She knows r1, that's what she picked. She can raise b to the r2 to the power r1, and that's going to give her b to the r1 times r2. On the other side, while she, as a message, got b to the r1, she knows r2, of course. So she's going to raise this b to the r1 to the power r2, b to the r1 times r2. Right? And that's it. And that will be basically the secret key that they share. Right? The adversary sees all of this. I mean, he could multiply b to the r1 and b to the r2, but that's only going to give him b to the r1 plus r2. That doesn't give him that. So hopefully this is secure. So there are two questions, of course. One is, okay, you can say, is this efficiently computable? Can the parties do what they're doing efficiently? That's important. And then the second question, is this secure or not? Is this efficient? Okay, so you want to pick some large prime number p. You could do that efficiently. So prime numbers are dense enough in the integers that if you were to just keep picking random numbers and checking if they're prime or not, you will, after a reasonable number of steps, find a prime number. Picking a generator, b in zp star, this is tricky actually. It turns out for this, you want to know the prime factorization of p minus 1. But, there are ways basically to do this efficiently. One note that I'll make is the p and the b here don't have to be actually random. Right? So this is like information that you're sharing with the world anyway. So there's no advantage of making this these numbers random. So, you can, there's a way to pick a prime p and a generator b efficiently and do this stuff. But, the details, I'm going to sweep it under the rug. Then you can ask, and, the other stuff, like picking a random elements here. That's easy to do. Exponentiation is easy to do, as we know. Is it secure? So we know the adversary sees P, he sees B, B to the R1, B to the R2. Now we are hoping, of course, from B to the R1, he can't compute R1. This is our hope that X is one way. Good thing is no one knows how to invert X efficiently. Bad news is proving this is at least as hard as proving the P versus NP. Right, because this actually function is in MP. So if you show that you cannot invert this function efficiently, you show P is different from MP. But that's not all, because actually this is not really the only way you could crack this system. So really, if you want to be more careful about it, what you should be saying is it possible to compute B R1 to R2, which is the secret shared by the two parties at the end of the protocol, from the knowledge of P, B, B to the R1, B to the R2. This is what the adversary sees. So that's really what you want. You want this to be hard. So this is called the Diffie-Hellman assumption. And we think, people think it's hard. But actually, that's not even really enough. What you really want is a decisional Diffie-Hellman assumption. What you really want is not that the adversary computes this exactly, but actually he or she does not learn anything about B to the R1, R2. Doesn't even learn the first bit of, let's say, B to the R1, R2. And this is called decisional Diffie-Hellman assumption. So lots of assumptions you have to make. And actually, this turns out to be false in ZP star, but you can pick other universes, other groups, candidate groups where this assumption hopefully holds. But yeah, that's the way you can do this secret key sharing. That's one way to do it. Now, in the remaining 15 minutes, I want to talk about the third part, which is like, let's just get rid of this key sharing business. Like, it's just inconvenient. Why are we doing this? And let's just do things in a more straightforward way. And this leads to what we call public key cryptography. Okay, so now here's the situation. You want to send me an email. This should be encrypted in some way, but I want to be able to read this email, of course. So how are you going to send me an email without us first engaging in this key sharing business? So first, let me actually describe public key cryptography in pictures. Okay? Using a picture, it's actually quite simple. Here's the idea. Okay, so let's say you're on this side, you're Marjorie, and you are expecting a message from someone else, let's say Cersei. What you do is you have a lock and a key that opens that lock. The key, you keep it secret to yourself. You don't share it with anyone else. But the lock, you say to people, OK, if you want to send me a message, use this lock to send that message. Use this lock to lock that message and then send it to me. So Cersei is like, OK, takes the lock, puts her message in the box, locks it with that lock, and then sends it. Now, I'm the only one, hopefully, who has the key, right? So I can open it. But hopefully, no one else will be able to open that box. That's basically the idea. Of course, now you have to convert this into mathematics and into an algorithm that implements this. And that's going to be our task. But first, let me just say that, in general, we don't think of this lock as a lock, really, but we call it a key. So think of this key as a key that can be used to lock a message up, but it cannot be used to unlock that message. Okay? So we think of that lock as actually a key. That's why it's called a public key cryptography, because this key is going to be public. And people who want to send a message will use this public key to lock their messages, to encrypt their messages. But this key cannot be used by an adversary to unlock that message. It's a one-way key in that sense. Now, in notation, we can say, okay, M, let's say M denotes our message. Let's say K sub pub is the public key that anyone can use. And K private is the private key. What you do when you want to send a message, you take the public key and the message M, you have some encoding algorithm, you get some ciphertext out of it. You send that ciphertext encoded text through the channel. And then at the other end, you take that encoded text, you take your private key, you have some decryption algorithm, and you get the message M back. Again, if you think about it, you want this encoding to be in some sense one way, right? You don't want the adversary who sees C to be able to recover the message. The problem is that before, what we said is to ensure this one-wayness, we could use the fact that the key here was private to that party. That's no longer the case, right? Now the key is public. So we cannot use the secrecy of this key to ensure one-wayness. What we're going to be able to do, though, is we're going to be trying to ensure its one-wayness using computational complexity, in the sense that even if the adversary knows the key and the C, it will be computationally infeasible for him to recover M here. Okay? Now, here's a little thing to notice, though. I mean, we're saying, it's one way, yes. But at the same time, at the other hand, I mean, we have to invert this function, right? We have to get M from C. Right? So it is one way in some ways, but it's also invertible if you know this secret key, private key. So these are called trapdoor one-way functions. There's a trapdoor. Okay. So I'm going to describe you now the RSA crypto system from 1977, which is like a very famous crypto system that, variations of it are being used today all over the place. Actually, they were not the first to discover this. So there's a guy called Clifford Cox who discovered it 3 years before they did. This remained secret until 1997, actually, because it was classified information. He was working for the British intelligence agency. It was classified. They didn't really know how to implement this system efficiently. So they didn't publish it or use it. But yeah, later on this was revealed. Okay, so for the RSA crypto system, we're going to use the RSA function now as our one-way function. Okay, what was the RSA function? We let n be some composite number. We fix some exponent. Again, think of the exponent as 3. Okay, let's just fix it to 3. So for some b in Zn star, so for some base, we're just computing b to the e. If e is 3, this is cubing b. So the cube function. Again, you know n and e, but you don't know phi of n. And if you think about it, your encoding function, now here you want, your encoding function is going to be this RSA function, okay? This hopefully one-way function. So you want b to correspond to your message m, right? Using this message m, we're going to raise it to the power e, m to the e. And what's going to be our public key? Our public key is going to be n comma e, because this is what we need to be able to compute this RSA function. We need to know the n, we need to know the e, but once we know the n and once we know the e, and we have our message, we can apply this function and do the encoding. Right? As we discussed, the inverse function, let's say if E is 3, taking cube root, seems to be hard. We believe it's computationally hard. But here's the remark that I made earlier. If you knew phi of n, you could actually do this inversion quickly. And that's actually great. This is great because this is the advantage that we need over our adversary. Right? This is what Marjorie is going to do to invert it, because she has to be able to invert this. Right? And how is she going to invert it? Well, she's going to invert it because she's going to know phi of n. Now, how do you, from phi of n, actually invert this? It's not hard. So what you can do is you have some fixed exponent e in z phi of n star. You can actually compute, if you know phi of n, you can compute the inverse of e in this universe. This is, let's say, exercise, homework. Okay. But once you have the inverse, right, then it's easy. I take b to the e. How do I invert it? I raise it to the power this inverse. b e inverse equals b, inverted. Okay? So this is exactly what Marjorie is going to do on the other side to decrypt. So again, why composite? When we choose an n to be composite? Because if n was a prime number, then phi of n would be known to everyone, to the adversary as well, and it wouldn't be secure. It wouldn't be one way. Okay, so this is our function. Again, as I said, we want b to correspond to the message m. We want ne to be the public key. So here is how the protocol is going to go from Marjorie's side. So what I have to describe to you is how do we compute what is the public key and the private key. And then what is the encoding scheme and the decoding scheme. Once I give you these information, then everything is there. Right, so first, what she does is picks two random distinct primes, p and q, and lets capital N be p times q. She computes phi of n, p minus 1 times q minus 1. She can do that, easy. Then she picks some exponent in z phi of n star. You know what? Think of E again as 3. Doesn't matter. And then she publishes n, comma E as the public key. Right? So if you want to send a message to her, you use this public key. Now, Cersei, when she wants to send a message, what does she do? She says, OK, my base that I'm going to use for the RSA function is going to be the message itself, m. And then compute the ciphertext, b to the e, okay, or m to the e. Raise it to that exponent e. Here's a little thing. And then you send, of course, that c. Here's another thing. You might ask, what if m is not in zn star? What if this base is not in zn star? Because that was a requirement. Turns out that it's OK. Even if it's not in zn star. But I'm not going to discuss that. But it's OK. So it doesn't break down because of this. Anyway, so she sends C. Now at the other end, Marjorie gets C, which is supposed to be b to the e, or m to the e, actually, right? The message to the power e. Needs to recover b, which is m, the base. And as I said, you compute E inverse in Z phi n star. That's your private key. And with that inverse, again, you know how you compute this exercise. But once you compute that, you can do B to the E inverse and recover B. Okay? So in picture, again, you know, Marjorie has picks two prime numbers, distinct prime numbers P and Q, computes N. She picks some exponent E in Z phi n star. Her private key is going to be the inverse of E. And the public key is going to be n comma E. When you want to encode a message M, what you do is you compute M to the power E in Zn star. You send that over, and your decryption basically takes C to the power E inverse, and you get back the original message M. So everything I just said. Is it efficient? Can you do things efficiently? Basically, the answer is yes. Although, again, I'm going to sweep this under the rug for now, because I don't have time. Is it secure? Well, it's, as I said, a variant of it is very widely used in practice, so it better, hopefully it's secure. The thing is, from n, as we saw, if you can efficiently compute phi of n, we can crack RSA exercise. And actually, if we can factor n, we can compute, turns out, phi of n. And in some sense, factoring and computing phi of n from n are computationally equivalent. Here's the thing, quantum computers can factor efficiently. So if you can build a quantum computer, you can break these systems. You can ask, is this the only way to crack RSA? So we don't know this actually. So it could be the case that you crack RSA, but at the end of the day, you don't come up with a efficient factoring algorithm or an efficient way to compute phi of n. So there can be other ways to crack this. So we're really hoping that it's secure. All right, thank you.